our great pleasure to have Darío García from University of the Los Andes, who's going to talk about pseudofiniteness and measurability of the everywhere infinite forest. Okay, so please welcome Darío. Okay, thank you very much.
Well, thank you very much, Masoud, for the presentation, and thank you, Rayhane and the group in Iran for the invitation to talk. As I was saying, it is always nice to be invited to Iran, even if in this case it's virtual. And yeah, so I had really good memories about my visit 4 years ago. So what I'm going to present today is, I mean, there are two topics mainly. This is about pseudofinite structures and measurability. But I mean, these are two concepts that have main definitions that are due to many people. And what I want to do today is basically present the definitions, and also present a case of study. And the case of study is what I'm going to define in a couple of minutes, and it's the everywhere infinite forest. So the two main results that I'm going to present today are joint work with an undergraduate student of mine here at Universidad de los Andes. Her name is Melissa Robles. And let's just start. So let's start first with pseudofinite structures. So the definition says that a structure M is said to be pseudofinite if, I mean, this is going, just to set up something, this is going to be first order logic. So what I'm going to talk about are first order structures and first order languages. And the structure is going to be pseudofinite if any of the following three equivalent properties hold. Okay, so one way to define a structure to be pseudofinite is that every sentence, every first order sentence that is true in M is also true in some finite L structure. Another way to define it is that M satisfies the fin L, which is the common theory of all finite L structures. Or the last one, and is probably the most useful one for me, is that M is elementarily equivalent to an ultra product of finite structures. Okay. So being pseudofinite, for me, the first condition and the third conditions are the essential ones, because usually what I do to show that something is not pseudofinite is to find a sentence that is true in M but is not true in any finite structures. And what I do to show that the structure is pseudofinite is to show an appropriate ultra product of finite structures that has the same theory as M. Okay. And a small observation regarding the last condition is that in general, we know that an ultra product of finite structures can only either be finite or must have size continuum, right? So the last condition is not M is isomorphic to an ultra product, but rather M is elementary equivalent to an ultra product, because we're describing structures that have similar properties, similar features. But for example, they can be countable, and that's the main part here. So usually an ultra product of structures in general is going to be very saturated, either finite and it's saturated because it's almost trivial, or it's infinite and has a lot of saturation, and it's also have a big cardinality. But one can also talk about countable structures that are pseudofinite because I'm just asking about elementary equivalence. Okay, so let's see some examples. So the first example that I'm going to show, and actually the first non-example I'm going to show is are some linear orders. So the linear orders of the rationals, do you see the hand when I point out here, perhaps? Are you seeing when I do like this?
Yes, we see it. Yes, it's correct. Yes.
Okay. So the linear orders of the rationals and the linear order of the integers are not pseudofinite. Why? Because if you have a finite linear order, it must be discrete, therefore it cannot be dense, and it also must have endpoints. So since being dense can be written in a sentence as a first order sentence, then Q is dense, and there is no finite linear order that is dense, therefore Q is not pseudofinite. And the order of the integers doesn't have endpoints, but you can say in a sentence that the linear orders must have minimum and maximum points. So these structures are not pseudo-finite. The field of the complex numbers is also not pseudo-finite. This is a little bit trickier, but the trick is noticing that there is a function that is definable, which is taking the squares, that is surjective because every complex number is a square of a complex number, but it's not injective because there are many complex numbers that have the same square, right? That can be written in a sentence. And that sentence cannot have finite models because if you have a finite field, or in general a finite set, and you have a function that is injective, that is going to happen is if and only if it is surjective, right? And so the point is that here you have a definable function that is injective but not surjective, and that's actually a very useful trick to show that the structure is not pseudo-finite. If you can find a function that is definable and is injective but not surjective, or surjective but not injective, then the structure is not going to be pseudo-finite. And the same trick can be applied, for example, for the group of the integers. You can have the function that x goes to x plus x. That function is clearly injective in the integers, but it's not surjective, and therefore this structure is not pseudo-finite. So these are examples of structures that are not pseudo-finite, and some examples of structures that are pseudo-finite. Well, the first example is almost by definition is that every ultra product of finite structures is pseudo-finite. So in some sense, it is very easy to create examples of pseudo-finite structures. Simply take a class of finite structures and take an ultra product, and then you have a pseudo-finite structure. Also, a very famous example is due to Axe. So he gave a characterization, an algebraic characterization of what it means to be a pseudo-finite field. So an infinite field is going to be pseudo-finite, meaning it is elementary equivalent to an ultra product of finite fields, if and only if it satisfies the following three conditions. So the first one is that K is perfect. The second one is that K has a unique extension of degree n for every n. And the third one is that K is pseudo-algebraically closed. And that means that it's almost like being algebraically closed, except that you ask that every absolutely irreducible variety over K has a K rational point. So every variety that is irreducible over the algebraic closure of K must have a K rational point. So these three conditions are all algebraic conditions on a field. And he showed in an outstanding work in 68 that the fields that satisfy these conditions can be characterized as having the same theory as an ultra product of finite fields. Okay. So some other examples, for instance, you can take vector spaces over FP. They are pseudo-finite because you can simply take the products of vector spaces. And there is a very nice example that I actually like a lot, and is the group R plus, or in general, every divisible torsion-free abelian group, right? They all have the same theory, the same complete theory. That's a very useful example in model theory. And one can notice that this is isomorphic, actually R plus, the addition group of the additive group of the real numbers is isomorphic to this specific ultra product of finite groups. You can take the prime cyclic groups with the addition, take an infinite ultra product, meaning an ultra product with respect to a non-principal ultra filters over the prime numbers. And that's going to be a torsion-free divisible abelian group, and therefore it has the same theory as R plus. And in fact, since we know that this theory is uncountably categorical, we know that R plus is actually isomorphic to this ultra product. Okay. And also, in the same fashion, one can have vector spaces over Q. They are also pseudo-finite. And that's a little bit weird because if you consider, if you think about the language here, the language is the language where you have one function symbol for every rational scalar. And it's impossible to have a finite Q vector space. But what actually happens here is that you can have finite vector spaces when you only are allowed to multiply by finitely many rational numbers. And then when you accumulate more and more scalars, in the ultra product, you're going to have a Q vector space. That's more or less the idea here. So the point here that I want to make is that sometimes what happens is that you have a lot of properties to, I mean, a lot of sentences that must be true. And what happens in the ultra products and in the finite structures approximating them is that more and more of these properties are true, but it is not necessary that you have a finite structure to satisfy all of them, right? Okay. So a very famous example is the example of the random graph. So in case you're not familiar with it, there is a famous theorem of Erdős and Renyi in 63, sorry. And they show that if you fix a number R and you think about these so-called Alice-Restaurant axioms, which are these axioms that says given two disjoint sets, there is a point that is related with all of the elements in one side and none of the elements on the other side. We're talking about graphs. Then they show that if you take a graph at random, meaning you have n vertices and you decide whether or not to put an edge between the vertices with some probability p, then the probability that these axioms, these Alice-Restaurant axioms are satisfied in this graph is 1, okay? And actually, this implies in particular that for every finite graph, the probability that H appears as an inducible graph of a graph chosen at random is also 1. It tends to 1 when n goes to infinity, right? This is a study about finite graphs. This is a result about finite graphs. And what Rado showed later, I mean, from the logic perspective, let's say, or from the infinite perspective, is that in fact, if you take these Alice-Restaurant axioms, there is only one countable graph that satisfies all of them, and that's what we call the theory of the random graph. That's a famous example of a structure in general in model theory. And the result of Erdős and Renyi actually showed that since these Alice-Restaurant axioms have probability 1, in particular, there is a finite graph that satisfies each of these axioms, and therefore the theory of the random graph is pseudofinite. That is one way to show that the theory is pseudofinite. Another related result is that, of course, then you know that the random graph is pseudofinite, but you don't really have a nice class of graphs such that the ultra product is the random graph. And that's kind of the other questions. One thing is to know that the theory is pseudofinite for any reason. And the other thing is to actually witness it as an ultra product of a specific and meaningful, interesting class of finite structures, right? And then in that sense, it's good to know that Bolovash and Thomason showed in 1985 that in some sense, every infinite ultra products of the so-called Paley graphs are a model of the random graph. So what are the Paley graphs? The Paley graphs are graphs defined in finite fields. And what you do is that you put an edge between x and y if and only if the difference between x and y is a square, okay? For that relation to be symmetric, you need to have q congruent to 1 modulo 4, okay? So that minus one is a square, and therefore this relation is symmetric. When you define this class of graphs, what happens is that, well, Bolovash and Thomason showed this result, which is basically saying that the Alice-Restaurant axioms hold there. So let me just read the result and talk a little bit about what is involved here, because it's going to be related with the topics later. So if you have U and W, disjoint subsets of FQ, Q congruent to mod 4, so that this graph works. And you have S, which is the set of non-zero squares in FQ. So remember that the two elements are going to be related if the difference is a square, okay? So you can ask for this set, the BUW, which is going to be the set of elements in FQ, such that X minus U is contained in S. what I'm saying here is that X is related with every element in U, right? Because all these differences are squares. And X minus W is contained in FQ minus S, meaning X is not related with any of the elements in W. So I'm asking for those elements that satisfy the Alice-Restron axioms from with respect to U and W, right? Fixed. That set is called VUW, and what happened is that you have this bound, which is here is the size of VUW minus Q over 2 to the M. M is the size of U in W. The difference between those quantities is bounded by 1/2 of this constant here. You have, actually, it just occurred to me that perhaps I can make some annotations. So you have these quantities here. Do you see what I'm writing here, perhaps? And then it's bounded by this number, okay? So this is a weird way to say, I mean, I know this is a weird bound, is almost exact as they showed, it's almost tight as a bound in combinatorics. But the important thing here is that what I'm saying here is that the measure of BUW is roughly 1/2m, right? Because the size of the structure is Q, sorry. And so what I'm saying is that the size of this element, of this set, is Q over 2m, except for an error that is of the order of Q, of a square root of Q. And therefore, when you divide by Q, what you're going to obtain is that the measure of this set over here, is approximately 1/2 to the m, plus something that goes to 0 when Q goes to infinity, right? So what happens here, I mean, another way of saying, of stating this result is to notice that now I have a specific class of graphs, which are called the Paley graphs, whose ultra products are models of the random graph, which I knew that it was pseudofinite on one hand. And on the other hand, I can explicitly bound the sizes of definable sets in these graphs. This is what I'm going to talk about today. I'm going to talk about how to show that something is pseudofinite and how to find appropriate classes of graphs so that I can have good control on the study of cardinalities of definable sets in the ultra products of finite structures. Okay. All right. So let me just erase what I just did here. Continue. Good. So now I'm going to talk about the theories which are going to be the study cases of today. So I'm going to call them theories of tree-like graphs, and just because I want to avoid the usual confusion, because when you talk about trees, a lot of people think about order structures immediately, and it's completely natural. Here today, what I'm going to talk, when I talk about trees, and when I say tree, what I mean is a simple graph that has no cycles, okay? So it's a tree in the graph theoretic sense. So that's why I also call them a tree-like graph. So a tree simply is a simple graph, no loops, no multiple edges, without cycles. And notice that this property can be axiomatized in the language of graphs by an infinite theory, okay? So it's a theory that says there is no loops, the relation is symmetric, right? So, and this part is basically saying that there are no cycles of size n, right? You can write in a sentence that there are no cycles of size n, but then you have to run n from 2 to infinity to say that there are no cycles at all, right? And this is a theory. It's not complete, of course, because it might depend of more properties about the possible trees that one can have. And then you have immediately, once you define a theory or you define a class of structures, you have a very initial question or very naive question, which is which kind of infinite trees are pseudo-finite, okay? For example, if you have the theory of graphs, you can ask also which kind of graphs are pseudo-finite or which kind of structures are pseudo-finite. That might be a little bit too wide of a question, especially because this theory is not complete. So it's very difficult to check all the possible completions and check which of them are pseudo-finite. Okay. For more algebraic structures, it's a bit easier. And in general, I'm interested in this question, although I know it's a little bit too wide. So partial answers are also welcome, at least from my point of view. And perhaps less wide, and it's also a question that we were working with Ali in Paris, is, okay, I actually believe that every infinite tree that has bounded diameter, the diameter meaning the maximal possible distance between any 2 points, if you bound the diameter, I think it's going to be pseudo-finite. I haven't found the proof, but I think it's true. Okay, so this is the kind of questions that one can ask every time you have a nice class of objects. You can ask, well, which of them are pseudo-finite, and if some of them are and some of them are not, then it becomes a very interesting question. Perhaps too difficult to solve, but still interesting. Okay, so let me just put an example. So you have here a very easy, very canonical example of a tree. It's basically a rooted tree that's split in 3 points. So you have the root, 3 successors, from each of these successors another 3 successors, etc., etc. It turns out that this countable tree is not pseudo-finite. Why? Because we can find a sentence that is true in this graph, but in this tree, but it's not true in any finite graph in general. And what is the sentence? The sentence basically says that there is a vertex of degree 3 and the rest of the vertices have degree 4, okay? Which is the root has degree 3, the other points have degree 4 because there are 3 successors and 1 predecessor, let's say. And the point is that that sentence, which is a sentence in the language of graphs, can be written in the language of graphs, cannot have finite models due to the handshaking lemma. Recall that the handshaking lemma says that if you sum the degrees of the vertices in a graph, in a finite graph, it has to be twice the number of edges. Why? Because if you sum the degree of the vertices, what you are adding is all the possible edges that go out from a vertex. And an edge has 2 endpoints, and therefore, when you sum all the degrees, what you are doing is actually counting every edge twice. And this is a very initial, very preliminary result in graph theory. And what happens in this case is that if this sentence has a finite model, it should be a graph. And when you add the left-hand part, is going to be 3 plus 4 times something, which means it's going to be an odd number, and it cannot be twice the number of edges, right? That's how you show that this sentence doesn't have finite models. And in fact, you can, it is possible to analyze which sentences of the 4 P, Q, R have finite models. And one can see, although I'm not going to do that today, that basically the only obstruction is the handshaking lemma. Once the handshaking lemma is not an obstruction, meaning once there is a possibility that the left part is an even number, then there are models of that sentences. Okay. However, I'm going now to define, this is the case of study of today. So I'm going to define what I call the R regular graph and the everywhere infinite forest, okay? So the R regular graph is simply an infinite tree that such that every vertex has degree R. That's it. So in the left here, you have an example of T4, which is going to be a tree such that each vertex has 4 neighbors, and that's exactly what happens here. And in contrast, the theory T infinity, or also known as the everywhere infinite forest, is the theory of an infinite tree in which every vertex has infinite degree, right? And here, well, there's an artistic representation by myself of such a model that I call sponge. Why is it called the everywhere infinite forest? Well, everywhere infinite because it is infinite and every vertex has infinite degree. And the point is that since being connected is not a property that you can define in a first order theory, what happens is that you can have the tree, but then the saturated models of that theory are going to be forests, are going to be different trees, different connected components. Same thing happened with TR. Okay, there is let's say the atomic model. The initial model is only one tree with these connections, but then the saturated models are going to have different components. Okay, so these are very famous examples of structures in model theory, and they have been studied. So, for example, one of them, I'm going to show some of the properties here, although I'm not going to use all of them. So first of all, there is the theory TR, which is axiomatized by the theory of being a tree, meaning being a graph without cycles, and every element has R neighbors. And infinity is the theory that says, oh, I didn't complete the sentence here on the right, but it's basically there are no cycles and every element has more than n neighbors for every n less than bigger than 1. Therefore, there are infinite neighbors. The point is that these theories are complete, and the way you show they are complete, for example, is showing that they have quantified elimination in an expanded language. And the language is this L prime, which is given by binary predicates dn. And the interpretation of these predicates is the following: is dn x y holds if and only if the distance between x and y is equal 1. So remember that is equal to n, sorry. So remember that when you are in a tree, when you are in a graph without cycles, given any 2 points, either they are connected or they are not. But when they are connected, there is a unique path that connects them. And therefore, you can define these distances. When you add these new symbols to the language, then the theories, both theories have quantified elimination. And as I mentioned before, both theories have atomic models. And quantified elimination plus atomic models is a way to show that the theory is complete, right? So both theories are complete. And in fact, TR is going to be strongly minimal and also uncountably categorical, right? Moreover, you can describe the algebraic closure in models of TR very easily. This theory is going to be disintegrated if you're familiar with the trichotomy principle. And that means that the algebraic closure of a set is basically the union of the algebraic closure of each of the elements. And the algebraic closure of an element is simply the whole tree that is in the connected component of A. So therefore, this union is actually equal to the connected components containing vertices from A. And that's a completely accurate description of the algebraic closure in models of TR. What happens with infinity is a little bit more difficult. The theory is going to be omega stable, but it's going to have Molly rank omega, right? And the reason is that what happens is that whenever you have a vertex, the ball around it, the elements are at distance 1, form a set of Molly rank 1, okay? And then the elements that are at distance 2 form a set of Molly rank 2. Why? Because the elements at distance 2 must be associated to an element at distance 1, and there are infinitely many of them for each element at distance 1. That's basically the classical way to show this. And then what happens is that the further away you go from the vertex, the bigger your Morley rank is. And if you consider the type that says, I'm not at finite distance from A, that type is going to have Morley rank omega, and it's actually going to be the stationary type in this case. So there is a very good description of these theories and the models of them. And what I find really interesting is that, of course, these are case studies that I saw the first time when I took the course in model theory and of course in these topics. Then I learned about pseudofiniteness, and then, well, it turns out that these theories are also going to be pseudofinite, and that's the next slide. So the point is that, so the first thing that I want to mention is that these theories are pseudofinite, and the way you show that they are pseudofinite is very similar to the way you show that the random graph is pseudofinite. So remember that what we did for the random graph was first noticing that there is an axiomatization of the random graph, meaning the Alice rested on axioms, and then trying to find an ultra product of finite structures that satisfy that theory, right? And therefore, since the axiomatization was a complete theory, the two structures are elementary equivalent, and therefore it is pseudofinite, and that's it. So the proposition is actually very easy. There is not much to say there. Well, except for the existence, but let me just say the proposition first. So imagine that you have a class of finite graphs, Gn, and in the natural numbers, such that each graph Gn is R regular when R is fixed, or Dn regular in the other case. So these graphs are regular graphs, meaning all vertices have the same degree. All vertices have the same number of neighbors. And also the girth goes to infinity. Remember that the girth of a graph is the length of its minimal cycle, okay? So the minimal cycle, you take the length, that's the girth, and I'm asking that thing to go to infinity. Oh, okay, perhaps I should have mentioned something before. So let me just go back here, actually, yes. And then, I mean, if I don't say this coming now, then probably what I'm going to say later doesn't make any sense. So what I want to say here, okay, yeah, I get it. Notice that there was this question of which kind of infinite trees are pseudofinite. And when I first asked myself that question, my first answer that convinced me for almost 2 years, because it was actually it looked very neat, is that, well, there are none. And the reason is that if you think about the finite trees, every finite trees have vertices of degree 1, right? Every finite trees have leaves, and therefore there are vertices of degree 1. So none of these examples we're gonna be pseudofinite. That's what I thought at first, and then I just forgot about the question. But then I realized that there is a mistake with that answer. And the mistake that I have is that, well, being a tree is satisfying this theory. And to satisfy this theory, you must satisfy an infinite number of axioms. So what could happen is that you can have an ultra product of finite graphs that have cycles of length bigger and bigger, right? So what happens is that there are no cycles of length 3 because at some point I don't have cycles of length 3. Then there are no cycles of length 4 because at some point in the construction there are no cycles of degree 4, and so on. So if I just make the cycles bigger and bigger, what happens in the ultra product is that there are not going to be cycles. The cycles are going to be destroyed, right? And that's exactly what is going to happen here. So if you have a family of graphs, each of them is regular, and the girth, the length of the minimal cycles, is growing to infinity, what happens is that every infinite ultra product of graphs in this class is going to be a model of TR if this R is fixed, or if the n is going to infinity, then it's going to be a model of T infinite. That is very easy to prove because what you show is that they are graphs. Yes, they are graphs. What about the cycles? Well, the cycles are going to infinity, therefore it's going to be a tree. And then every element, since Gn is R regular, every element is going to have R neighbors. Therefore, it's going to be a model of TR. Or in the other case, every element is going to have infinitely many neighbors because at every stage, the number of neighbors is the same, but it's growing bigger and bigger, and therefore in the ultraviolet it's going to be infinity, right? So they satisfy the common theory. If I find classes of finite graphs that satisfy these two conditions, that's all I need to show that TR and T-infinity are both pseudo-finite. And what I'm going to do now is to, well, I mean, the result that we have with Melissa Robles is that, well, actually such classes of finite graphs exist, right? There are classes of finite graphs that are regular and the girth is going to infinity. And so this shows that, in particular, that both of these theories are pseudo-finite. Okay. So this is the thing. I started studying some very specific example in model theory, and then when you see the proof, what you're gonna see is that it actually involves a bit of combinatorics. So how much time have I used so far? Probably half an hour. So
yeah, I think around 40 minutes, something like this.
okay. So
well, I mean, we have two options. Either we can have for 10 minutes break and you can continue for another 50 minutes, or we can continue for 1 hour. It depends to you. I mean,
yeah, I'm going to take the option of the break, but let me first, I will just check in if I have time to do a little sketch of the proof, just to leave you with some idea of it. So you should see now like a notebook or something. Is it correct?
Right.
Correct. So I'm going to show this part. I mean, I'm going to show how one see that such classes of finite graphs exist. Okay. And the construction is very interesting, actually. It's called the lifting. So what happens is that there is some construction in combinatorics called the lifting of a graph, in which you start with a graph H and you end up with a graph LG. Sorry, you start with a graph G and you end up with a graph LG, okay? So how do you construct this lifting? Well, it turns out that the graph is given by vertices and edges, and then the new vertices are going to be the following. They are V times 0, 1 to the number of edges. Okay, so each vertex of the lifting looks like a vertex in the original set, and then a function that goes from the number of edges to 0, 1. Okay, or if you are into topology, you can think about -1 and 1 and think this function as orientations of the edges. This is the set of vertices, and I'm going to say that BF is related with WG if and only if first, well, B is connected with W in the original graphs, and F restricted to, okay, let me put a name to that, please. This is an edge, and F restricted to all edges different from E, and G restricted to all edges different from E are the same. And also what happens is that F of E is different from G of E. Okay. So this, I know this sounds a little bit weird, and the number of vertices is going to explode dramatically, especially if you have a lot of edges. But the interesting thing about this construction is the following. If you start with a graph G, then, well, let me just say here. So if G is, let's say, D regular, then the lifting is going to be D regular too. Okay? And this is the most interesting one. If the girth of G is K, then the girth of the lifting is 2K. So what I'm doing with this process is increasing a little bit the girth of the graph. And let me just put a little bit, give a little example just to see more or less what is going on. If you imagine that this is G, then what happens with this cycle, at least, let's say the cycle is ABC, is that, well, you have now 3 edges and you start checking what happens with these 3 edges, right? If you start with A0, 0, 0, which is a vertex and a function of 3 elements, then it's connected with B. Let's put a name here. So let's call this A1, A2, and A3, okay? So this element, A00, is connected with B because A is connected with B. And here I have to put 1, 0, 0. See? So notice that the tuple of zeros and ones is precisely the same. They only differ in the first component because the edge AB is the first edge, right? That's kind of the point. Then it is connected with C, 1, 0, and then 1. I have to change the third component. Then it is connected with A, 1, 1, 1. You see what happens? I started with A, I end up with A, but all the numbers have changed from 0 to 1. Then it's connected with B, 0, 1, 1. Then it's connected with C, 0, 0, 1. And finally, it is connected, 0, 1, 0. And finally, it is connected with A0, 0. So what happens is that this triangle, when I first run the cycle, the cycle that existed originally in G, it changes all the numbers. And then to go back, I have to rechange the numbers again. And that's why the length of the cycle is duplicated. And with that technique, then the rest is easy. Because what you do is, okay, what is Gn? You want it to be a regular, and you want the girth to be bigger than n. Well, in that case, start with kr plus 1, the complete graph in r plus 1 vertices. Of course, it's r regular because each element is connected with everybody and therefore has r neighbors. And then apply the lifting n of times. You can say n times, and you can say k times such that 2k is bigger than n. So the girth here at the beginning is 3. And then when you apply the lifting is 6, and then 12, and then blah, 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 until at some point is bigger than n. And that's all I need. I stop. When I do this process for every n, then I end up with our regular graphs whose girth is bigger than n, and then it's going to infinity. Or if you change this r by n also, then you have the n regular graphs. They are all regular graphs. And also the level of regularity is going to infinity. And then that's how you get these classes of graphs that satisfy the theory of TR and T infinity. And that's how you show that these theories are pseudofinite. Okay? Are there any questions before I move back to the presentation? Okay, then stop sharing this and continue sharing their presentation. Okay, so, we have shown that TR and T infinity are pseudofinite, but why do I care about pseudofinite structures? Why do I care about pseudofinite structures in the first place? Well, the nice feature of pseudofinite structures is the fact that the counting measure on the class of finite structures can be lifted using Wash's theorem to give notions of dimension and measure in their products. Okay? And that gives you a connection between finite structures, which is the class that you're analyzing originally, and infinite structures. And all these techniques of measure theory for infinite structures can be applied in the ultra product, and that can give you qualitative properties of classes of large finite structures. Okay, and that's kind of the point of view. Also, if you really check about quantitative properties of the class of finite structure that you're analyzing, often they induce desirable properties in the ultra products. We're gonna see a little of those later. But from the point of view of getting qualitative results for the class of finite structures from the ultra products, there is actually a lot of work from many different people, and that's actually how I got interested in these topics. So, for instance, there is a proof of the Semeres regularity lemma using ultra products. That's due to Goldberg and Tausner. There are some very interesting results about what is called the Freiman conjecture for non-abelian groups. So the Freiman conjecture was this family of results actually in abelian groups that basically said that if there is a bound on the doubling number of a subset of a group, of an abelian group, then it's because the subset itself contains a lot of additive structures, right? And probably the first results in the directions of non-abelian groups that were done for general classes, for classes of matrices and for linear groups, were done to Huchovsky. And the paper and the results are amazing because the idea is very simple: is using ultra products of finite structures and using something in the ultra product to say to pull back results on the families that you are taking the ultra product of. But the techniques that he uses in the ultra products are actually local stability, right? It's a very amazing paper. If you want to read, I really suggest it, really encourage it. Also, even Terence Tao uses this kind of approach to get some results on what they call expander maps for finite fields of large characteristic. And the way he showed these results was taking finite fields, taking an ultra product of those, and then checking the results in the ultra product and pulling them back to the class of finite fields. And more recently, there's a study of stable graphs and the Erdős-Heine conjecture for stable graphs. They are done via ultra products, and the results are due to Malyari-Sashela first, and Chernikov and Starchenko in a more modern presentation using pseudo-finite dimensions. So my point here is that it makes sense to study finite ultra products of finite structures in order to solve problems in combinatorics or in algebra when you talk about classes of finite structures on one hand. And on the other hand, this information that you obtain about ultra products sometimes can give you information about the class of finite structures, right? That's like a second step. Once you get the good information, the good model theoretic information of the ultra products, you can pull it back to the classes and try to say whatever meaningful say you can. And this first bullet here, when I talk about the counting measure and the class of finite and how it can be lifted to measure and dimension in the ultra product, I'm going to actually define it here. So what do you do for the ultra products of finite structures in order to get measurability, in order to get sizes of definable sets? Well, you start with the first order language. And you start
Darío, sorry to interrupt you. Yeah. Do you like, when do you think it's good to stop for?
I think these 2 slides and that's it. That would be a good point to stop.
Okay. All right.
Okay. So you start with the first order language, and you start with a class of finite L structures, and you an ultrafilter, and you expect the sizes of the structures to grow to infinity with respect to the ultrafilter. Then you can take the ultra product, okay? And what I'm going to show is basically just, there are many ways of doing it, but this is just a way to tell you how it is possible to talk definably in some expansion of the language about the sizes of definable sets in this setting, in the ultra products of finite structures. So what you do is that you enrich the original language, to a 2-sorted language, L+. It's going to have the original language D, and it's going to carry a language of order fields. So addition, multiplication, 0, 1, and less than, okay? And for every formula, there is a function symbol that we add to the language. And the point here is that whenever you have a finite structure, you can put that as a first sort, and in the second sort, you can put the real numbers. And then you can interpret these new function symbols as the following. You take b, which is an element in I to the y, to the length of the tuple y, and then that defines a set, which is phi mxb. That's a finite set. You take the cardinality, and that's going to be a real number. Okay? That's how you do the interpretation. Then you have the second sort with the language of order fields, the first sort with the original language that it has, and these so-called counting functions. I call this the counting functions, and this is the counting pair for me. Then you take a full ultra product of that thing. So an ultra product of that thing is going to look like this. It's going to look like a ultra product of finite structures in the first part, like the non-standard reals in the second part. And for every definable set, you're going to have functions that they're called the non-standard cardinalities of such definable sets. Okay? And the good point of taking the real numbers, I mean, you could actually take the natural numbers, but the advantage for me, at least, to take the real numbers is actually triple. First of all, you can talk about the standard part of different quantities that you can take, right? And pull back from non-standard reals to the actual real numbers. So you can have actually real valued measures on the ultra products. That's one thing. The second thing is that you can take quotients. And by taking quotients, you can also take counting measures. You can start comparing different definable sets with respect to a single definable set that is distinguished, and you can stay from the beginning. And the way to take this is the following. You take the measure of x with respect to d is simply x intersected with d, that's a definable set. The non-standard cardinality of that's going to be a non-standard real number. You divide by the size of d, which is a non-standard real number, and that's going to be a non-standard real number between 0 and 1. You take the standard part of that's going to be an actual real number, and that gives you finally additive real value probability measures on the product. And that's actually what you show. So once you do this, then the natural question would be, okay, is there a way to characterize sizes of definable sets in the ultra product of finite structures? And also, what do I require from the classes to have a control on the definables, on the sizes of definable sets? And what kind of properties these control definable sets can give me on the classes of finite structures? That's going to be that's going to be my focus on the second part of the talk. So this is a good point to make a break. We're going to start next with this slide.
So you could start. Okay.
All right. So the second part of the talk is going to be more focused on what kind of possibilities do we have when you are measuring cardinalities of definable sets in ultra products of finite structures. Okay. And probably the second part of the talk is going to have a little overlap with the talk that Dougal McPherson gave here in July in the seminar. Mainly the main result or the main definition here is that of asymptotic classes and measurable structures. The presentation that I'm going to give is a little bit different in order, and you're going to check this with the years whenever they are available. If not, I will tell you. But let me start with this theorem that appeared in a paper published by Anand Pillai in 2015, and it's about strongly minimal ultra products of finite structures. Okay, so imagine that M is an ultra product of finite structures that has a strongly minimal theory, and we're going to fix alpha. So alpha is going to be a non-standard real or a non-standard natural number, and it's going to be the pseudo-finite cardinality of M. Okay, the non-standard cardinality of M. Then what happens is that for every definable set X of M to the N, several variables, there is a polynomial with integer coefficients that has positive leading coefficient and such that the cardinality of x is precisely the polynomial evaluated in alpha, okay? Moreover, when this happens, then you can actually measure the Morley rank of x. Since we are in a strongly minimal setting, every set has finite Morley degree, and this polynomial is also calculating the Morley degree. If you take the degree of the polynomial, it's going to be exactly not the Morley degree, but the Morley rank of x. The degree of the polynomial is the Morley rank of x. That's the point. That's the first part. So every definable set has a non-standard cardinality that is actually a polynomial with integer coefficients evaluated in the cardinality of m. That's one thing. And the second part is a little bit more interesting. The second part is that whenever you have a L formula, phi xy, there is actually a finite number of polynomials, p1 to pk, and a finite number of formulas, psi1 to pk, such that first, the psi formulas are a partition of the y space. And what I mean with that is that these formulas, these defined sets that are a partition of m to the length of y. That's what I mean when I say the partition of the y space. And second, and this is probably more useful when to understand the first part, is that for any tuple A, when you consider the definable set defined by the formula phi with those parameters, the cardinality of that set is going to be precisely the polynomial pi evaluated in alpha, if and only if m satisfy the formula, the tuple of parameters A satisfy the formula psi, okay? So this is a couple of, what is going on in this theorem is, and is going to be actually a definition a little bit later, is two things. First of all, an accurate description of what possible cardinalities, non-standard cardinalities, the definable sets could have. In this case, polynomials with integer coefficients evaluated in the non-standard size of the model. That's one thing. And the second part is the so-called definability clause, which is basically giving a formula. When I vary the parameters, well, the cardinality of that definable set can vary, but it can take one of finitely many possibilities. And each of the possibilities is governed by a formula, meaning take the definable sets, take the parameters, depending on which of the formulas is satisfied by the parameters, then I know exactly what is the cardinality of the definable set. That's the issue. So that's a result that appeared in a paper of 2015 by Anand Pillai. And just to give a little example, this is a very easy one, but then a little bit later, I'm going to show a more difficult one. If you take M, which is the R plus or the ultra product of these groups, and we're going to consider a very easy formula. The formula is phi x1, y1, y2. So phi xy, let's say. And the formula is x equals to y1 or x different from y2. Then when you think about the non-standard cardinality of this, it can have two possibilities depending on whether A1 or A2 are equal. If A1 is equal to A2, then the realizations in the variable x of this formula are all the elements, and therefore the cardinality is alpha, the size of the whole set. But if A1 and A2 are different, then the realizations of these are going to be all the elements that are different from Y2, from A2. And that's going to be alpha minus 1. So notice the thing here. The thing here is that is a polynomial evaluated in alpha, in this case alpha or alpha minus 1. It's true that alpha is infinity, but it's a non-standard real number. So alpha and alpha minus 1 are two different numbers, right? One distance apart. And these two possibilities, alpha or alpha minus 1, depend on conditions, definable conditions that only depend on which were the parameters that I was using. That's the nature of this example here, okay? So polynomials, the possible cardinalities are polynomials, and they depend on definable conditions that only depend on the parameters that you're using. They do not depend on the set of realizations. Okay. And notice also, although in this case it's a little bit silly, that the degree of both polynomials is 1. And the reason is that this kind of formula always defines cofinite subsets of n, and therefore the dimension is 1, or the Molly rank is 1. Okay, so this is a very preliminary result. And another example that we can use concerns the theory TR. Okay, in the theory TR, we know that you can have an ultraproduct of finite graphs that is a model of TR. And then you can consider the formula not being at distance 2. X and Y are not at a distance 2. Okay? So in this case, when you replace this Y for a vertex, the elements that are not at distance 2 are all the elements except those that are at distance 2. And those that are at distance 2 can be counted very easily. Is from A, there are R neighbors, right? And each of those neighbors have R minus 1 neighbors, because you have to take out R, A, that are at distance 2 from A. So once you take all the elements except those R times R minus 1, which are finally many, that's going to be always the cardinality. In this case, for this formula, it never changes. However, when you consider the formula D2xy1, meaning x and y1 are at distance 2, and x and y2 are at distance 3, then some possibility appeared. Some other possibilities appear. Okay. Okay. I'm not going to consider the last one, although it's written here. But I guess to explain this, it's easier to make a picture, although I hope it looks well when I do it. So the point here is that there are these 3 possibilities. Why? Because it could happen the following. It could be x, this could be y1, and this could be y2, right? So if y1 and y2 are at distance 1, then the possible elements are all these elements that appear. So all the elements that are at distance 2 from y1 except this direction, right? That's why this is the number. It's actually r minus 1 square, sorry. Because it's r minus 1 neighbors of y1, each of which has r minus 1 possibilities, right? So it's r minus 1 square. I made a mistake here. That's one possibility. The other possibility is to have x, y1 here, and y2 on the other direction. In this case, since we're in a tree and y2 and y1 are at finite distance, x is unique. So this is not r, this is 1, right? The number is 1. There is only one possibility. If y1 and y2 are at distance 5, then there is exactly one point that is at distance 2 of y1 and distance 3 of y2. And finally, if you don't have any of these possibilities, meaning the distance between y1 and y2, or a1 and a2, is not 1 or 5, then there are no indices of this formula. It is impossible to have a point that is a distance 2 of y1, a distance 3 of y2, but y1 and y2 are not distance 1 or 5. Okay, that's kind of the possibilities. So what I want to check again is precisely this. So there are finally many possibilities for cardinalities, right? Finally many cardinalities. In this case, because we are in a strongly minimal theory and because these sets define finite sets, well, they are finite numbers, but they are given by definable conditions. Okay, this is the setting here. So this is what happens in general in strongly minimal ultraproducts of finite structures. But these are nice properties that one can isolate. One can have finally many possibilities for cardinalities depending on finally many formulas. This was in 2015. Let me just erase the pictures here and move to the next slide, because then we're going to go back. And to go back is to talk about asymptotic classes. And the beginning of the birth of asymptotic classes actually is in, I guess, is in 1992 with an outstanding theorem of Zoe Chatsidakis, Lau van den Dries, and Angus McIntyre. And I'm going to read it, but with a little less words than the one that are written here. It can be seen as a generalization of the Langevin estimates for finite fields. So the Langevin estimates are very similar to the ones that we showed here, but these work for varieties defined over finite fields. These are not only varieties, but definable sets over finite fields. So given a formula in the language of rings, and the formula can have many object variables and many parameter variables, then there is a positive constant C and finally many pairs, di and mu I. These di's are natural numbers between 0 and n, because n is the number of object variables, and these mu i's can be positive rational numbers. So given the formula, there is a constant and finally many pairs, such that whenever you take a finite field fq and parameters from that finite field, you consider the set defined by in that finite field for these parameters. And what happens is the following. The difference between the cardinality of the definable set and mu I times q, the size of the field, to the di, is less than c times q di minus 1/2. Okay? So whereas, I mean, again, as we did for the random graph and for the Paley graphs, this looks a little bit odd like this, because I mean this is coming from the Langevin estimates. But another way of reading this is saying, okay, given the formula, there is a constant and there is finally many pairs of possible dimensions and measures, such that for every finite field and every parameter, the size of the definable set is roughly mu I times the size of the field to the di, except for an error that goes to 0 when q goes to infinity. So this is a result about finite fields, but when you check the two products, what we are saying is that, okay, the definable sets in the ultra product of finite fields are going to have positive measure in some possible dimension, right? So a dimension that is a natural number and a measure that is going to be a rational number, but it's going to be fixed and it's going to work well in the ultra product. Not only that, but for every pair of possible dimensions and measures, there is a formula, psi, that tells you exactly when what is the dimension and measure that you take. Meaning, if psi holds for some tuple, then the definable set defined by that tuple has dimension di and measure mu I. This is the original result, the seminal result of Chatsidakis, Van den Dries, and McIntyre. And perhaps more or less 20 years later or 16 years later, it comes this definition. This is 2008. Is the definition of the so-called one-dimensional asymptotic classes, okay? So the idea is in essence the same. So let C be a class of finite L structures. We say that C is a one-dimensional asymptotic class if for every formula in one variable, okay, there is a positive constant C and a finite set of possible real measures, such that for every structure in the class, either it is uniformly, it defines, and for every set of parameters, it defines a set of less than C, so it is uniformly finite, let's say, or it has some positive measure. And what I mean with positive measure is this. the difference between the cardinality of the definable set, which is finite, and mu times m is bounded by this number. And not only that, but also for every possible measure, there is a formula telling you exactly which of the measures is taken. Let's stop right there for a second, because I know this is a difficult, I mean, it's an involved concept, but there are a couple of things here. This one-dimensional, well, this one over here, and is not talking about the possible variables. It doesn't have to do with it. It comes from the fact that it is either, so phi m a is either finite or dimension 1, okay? So the point is that whenever you talk about dimensions, one is usually thinking about natural numbers. So for us, it's like 0 or 1, and of course. But this concept can be generalized to the so-called n-dimensional asymptotic classes, in which in one variable, you can have dimensions, fractional dimensions. You can have 0, 1 over n. For example, you could have a definable set that defines a set of cardinality, a square root of the model, right? Until n over n, okay? So these are all in one variable, but even in one variable, you can have a predicate that defines part of the set that is not going to be uniformly finite, but it's also growing, but it's also not the full set. It grows, for example, at the level of a square root of the cardinality of the model. That's when the n-dimensional asymptotic classes come, and that's a definition of Richard Elves, who was a former PhD student of Dougal Macpherson. But what is true here is that the result of Chatsidakis, Van den Dries, and McIntyre is that finite fields are a one-dimensional asymptotic class, right? And this may come as a surprise, because if you remember the last slide, I was talking about formulas with many different object variables and parameter variables. However, a feature that is always present in this kind of definitions is that if you prove the result for formulas in one variable, then the result for formulas in n variables holds, right? So it is enough to show everything in just one variable. All right. So, which are, okay, this is the definition of asymptotic classes of finite structures. And now there are some definitions. Let's see. So as I mentioned before, the class of finite fields is a one-dimensional asymptotic class that was shown by Chatsidakis, Van den Dries, McIntyre, and is basically their theorem. Also, the class of finite cyclic groups is going to be a one-dimensional asymptotic class that was shown by Macpherson and Steinhorn, and is basically, so usually it goes in two parts. First of all, you have to understand the ultraproducts or the limits of these structures. And for that, when you talk about ultraproducts of finite cyclic groups, then you have to use the quantifier elimination results due to 1-Millev. Once you know that, you check what are the possibilities in the finite groups, and that's your answer. So that was shown by Macpherson and Steinhorn. Richard Elves, in his thesis, he showed that the finite simple groups of fixed Lie type over finite fields, they also form not a one-dimensional asymptotic class, but are n-dimensional asymptotic class, where this n depends on the Lie type that you fixed. And Mark Wrighton, another PhD student of Macpherson, he showed that the class of finite fields with some, well, not the class of finite fields, but some classes of finite fields with the Frobenius automorphism are also asymptotic classes. In the same fashion as Macpherson and Steinhorn did for the finite cyclic groups, they also showed that the class of Paley graphs forms a one-dimensional asymptotic class. And the proof goes in two parts. First of all, you understand that the ultraproducts of Bailey graphs are models of the random graph. Because you have quantifier elimination in the random graph, you know that you only need to check certain kind of formulas, meaning the formulas in one variable that is X related with some elements and not related with other elements, and then use Bolovash and Thomason results to know that they have the corresponding bound. And if you check the bound, if you check the bound here, remember, the size of the definable set is one number, a measure, times the size of the set, except for some error that goes to 0. And if we go back to the slide when I was talking about this, is precisely this. The size of the definable set is one measure, which is 1/2m, times the size of the structure, except for some error that goes to 0 when q goes to infinity. So it's precisely the same kind of feature here. Okay. And some classes of residual rings are shown to be asymptotic classes. That's due to Bello Aguirre, actually, who was a former student also of Dugan Macpherson in Leeds. And the point here is that notice that we have here the full residual ring. D is fixed, and I have a fixed, and I vary P on the primes. Okay, I'm going to mention a similar example later. Okay, so these are examples of asymptotic classes, and as you can notice, there are some like meaningful example in combinatorics, meaningful examples in algebra. And what we do know about the two products is that having an asymptotic class can tell you something about the two products. So, for instance, and that's a theorem of Macpherson and Steinheim, if you take an infinite ultra product of structures in a one-dimensional asymptotic class, the structure is going to be super simple in the sense of model theory, and the SU rank is 1, okay? And similarly, if you take an n-dimensional asymptotic class and take an ultra product of structures there, if it is infinite, it's going to be a super simple structure of finite SU rank, and actually the rank is bounded by the n given in the definition. So that was the result before, in 2008. And kind of the point is that, the idea, once you understand a little bit better what is going on, and using some results that we obtained, myself with Dougal, Macpherson, and Charles Steinhorn obtained later, is that what is happening at the core of this is that each instance of dividing for formulas in one variable is witnessed by a drop of the so-called pseudo-finite dimension, okay? And the point here is that if you have one-dimensional asymptotic classes, you either have positive measure or you are finite. That gives you two levels, which is dimension 0 and dimension 1. And that's why you have SU rank 1. And similarly, if you have n-dimensional asymptotic classes, you have n possible drops of dimension. And since if each instance of dividing is witnessed by a drop of dimension, then you can have at most SU rank n, okay? That's kind of the idea here. And I'm going to, I include this definition just by the completeness of the presentation, but let me just say that there was an attempt of Macpherson and Steinheim to try to characterize the ultra products of asymptotic classes. So what they did was to define the so-called measurable structures. And the idea is that a measurable structure is a structure that has whose definable sets have some possible dimensions and measures satisfying certain properties, which are the properties defined here. So you want, if the set is finite, then the measure is actually, the dimension is 0 and the measure is the cardinality. But what I call definability and finiteness here is the same that I was doing for strongly minimal structures, which is given a formula, there are finitely many possibilities for dimensions and measures, and each of the possibilities is governed by a formula, is definable, or empty definable if you wish. And there was this Fubini property that they had that was always present, and is basically a way to do proofs by induction on the dimension. So what you have probably is easier if I do it with an example here, with a picture, sorry. is if you have a definable surjection, so you can see this as this being X going to Y, let's say, you can partition Y into what happens with the fibers. So for example, this is partitioned in 3 pieces, so that when you consider the fibers, the dimension is fixed and the measure is also fixed, right? So in each of these 3 pieces, the dimension is fixed and the measure is fixed. And then what this means in particular is that once I have all this information, there should be a way to measure the dimensional measure of X, basically by doing an integral. And that's why it's called the Fubini property, right? So what you do is, okay, what is the dimension? Is the maximal possible dimension, which is the maximal di that appears, the maximal di that appears here, together with the maximal dimensions in the bottom. And the measure is, okay, if I fix that maximum dimension, which is this C over here, then I can just add the possible product measures corresponding to those elements. So this should be an S here at the end. Okay, this was an attempt to try to characterize the ultraproducts of asymptotic classes. It turns out that every ultraproduct of asymptotic classes is a measurable structure, basically because it is an ultraproduct of finite structures. That's why Fubini property is going to hold very well, and because you have this definability and finiteness conditions in the class, and therefore that's why they hold in the ultraproduct. However, it turns out that there are certain measurable structures that are not pseudo-finite. So this is not quite a good description, but it's a good attempt at least. Okay. All right. So let me just erase the pictures here. And okay. So recently, more recently, there is some further work with of Macpherson and Steinhorn, but now also with Sylvie Anscombe and Daniel Wolf. And they define the so-called multi-dimensional asymptotic classes, okay? So it's becoming a little bit more and more tricky, but basically the idea is a fair critic of this definition. So if you really check here, what are the possibilities for phi of MA, you are going to see this is, or m to the n, sorry. Okay, it can be something. Roughly in the ultraproduct, not in the finite structures, but in the ultraproduct, they look roughly like mu times m to the d, right? So in some sense, what you can say here is that the possibilities for the cardinalities of definable sets are always a rational number or a real number times mu to the d. And this is a very restricted class of functions, of possible functions for the cardinalities of definable sets. So what they wanted was to create a generalized version of this, in which, okay, you have some control, you still have definability, you still have finiteness, but perhaps you're not so restricted about what are the possibilities of the cardinalities of the definable sets, okay? And that's why they came up with this definition of multi-dimensional asymptotic classes. So let me just read what the definition says and more or less say a couple of remarks on that. So you fix a class of finite structures and you let R be any set of functions from the class to the reals, okay? So you give me a finite structure and I give you what is the value of the function of the function, which is going to be a real number, okay? But you fix that from the beginning. And then we say that C is an R multidimensional asymptotic class, or RMAC, if for every formula there is a finite empty definable partition, right? There should be an empty set here. An empty definable partition of structures and parameters such that whenever I have, sorry, I just spoke Spanish for a moment. So for every formula, there is a finite partition on structures with possible parameters, right? And for each piece in the partition, there is a function, HP, right? Such that the cardinality of the definable set, given a structure, given the parameter, is precisely this HP evaluated in the structure, right? Well, not precisely, but the difference between these two goes to 0 when the size of M goes to infinity. That's a multidimensional asymptotic class. And a multidimensional exact class will be one when it's not that the cardinality is roughly HP of N, but it's actually exactly HP of N, right? That's a multidimensional asymptotic class. So you have a little bit more freedom on the possible R, on the possible functions that you use to measure the cardinalities of definable sets. And associated to the multidimensional asymptotic classes and to the multidimensional exact classes, there is a corresponding notion of generalized measurable structures, right? Which is the same idea. I'm not going to give the definition here, but it's the same idea of what do I need for a structure? I mean, what kind of properties are satisfied by the ultra products of structures in multidimensional asymptotic classes, okay? So with this new definition, which is, I mean, the current one that is working, and I think is working very well, very natural examples that were not previously asymptotic classes now become multidimensional asymptotic classes. So for instance, in a paper in the same paper that I mentioned before that I have with McPherson and Steinhorn, we show that the class of two sorted structures VFQ, where V is a finite dimensional vector space over FQ, we consider that class. And what we showed is that given a formula there is a finite set of polynomials in two variables. Here we call it V and F, with rational coefficients, such that whenever you take a structure in the class, meaning whenever you take a finite dimensional vector space and as the first sort and the second sort the field F, the cardinality of the definable set of phi xa is given by the polynomial evaluated in the size of the vector space and the size of the field. So what happens here is that in this two-sorted structure, a lot more things can happen than the usual one-sorted structure of vector spaces. Here, not only here the field is not fixed, the field is growing, and also the vector space is growing. And that double thing could make the structure to have Molly rank omega, right? So it's not finite SE rank anymore, but it's a natural structure. And what happens is that there is a good control on the definable sets. And now we are including some examples that may have rank omega, right? For example, the T infinity also have rank omega, and that's kind of the point that I wanted to make here. So this example was not originally an asymptotic class, and the ultra products were not measurable structures, but now it is a multidimensional asymptotic class, and the ultra products are generalized measurable structures. That's kind of the idea, to include more people. And also in the PhD thesis of Bello Aguirre, he showed that. So remember that before I was noticing that these kind of residue rings, not groups, but residue rings, when you fix the prime, they form a d-dimensional asymptotic class. Now, if you consider the classes of finite residue rings Z mod NZ, where N is the product of at most D primes with exponent at most D, meaning you have basically D primes to choose from and possible powers, that class of groups is not going to be an asymptotic class because the primes are different, right? Because the primes might be different. However, it is a multidimensional asymptotic class. Once you fix the number of primes and the number of possible powers that they can have, you have many indeterminates and you have polynomials with this number of indeterminates. But with those polynomials, there is a good control on the cardinality of definable sets and also on the cardinality of the definable sets in the ultra products. And that's kind of the point here, the important thing here. Okay, so perhaps to finish this, well, I mean, to start finishing the talk, I want to mention that the same thing happens with the everywhere infinite forest. So the examples of the infinity. We already knew by Pillay that since the models of TR are all strongly minimal, then there is a good control on, I mean, let me just go back to the result of Pillay to tell you exactly what happens. So the TR are examples of strongly minimal pseudo-finite structures, and therefore the sizes of the definable sets are given by polynomials evaluated in alpha, where alpha is the cardinality of M. And not only that, but given a formula, there are finally many polynomials and finally many formulas that tell you exactly which of the values are taken here. So the results that we have with my student Melissa Robles is a similar result, but for the everywhere infinite forest. Okay, so let's see equals Gn be a class of finite graphs, so that each graph is Dn regular, and both the Dn, the degree of regularity, and the girth of the graphs are going to infinity. Then we already know, because we showed it before, that if I take an ultra product of graphs in C, it's going to be a model of T infinity, of the everywhere infinite forest theory. But if we're going to fix two things. We're going to fix alpha, which is a non-standard integer corresponding to the cardinality of the graph, of the full graph. And this beta is going to be a non-standard integer corresponding to the cardinality of the degrees, you see? So this beta, I mean, when you can think of this about is, for example, thinking that the number of neighbors that each vertex has in the ultra product is beta, okay? And then what happens is that once you fix those two parameters, then for every formula, there is a finite number of polynomials, P1 of xy and Pk of xy. These are two indeterminates with integer coefficients, such that for every set of parameters, the cardinality of the definable set is given by a polynomial evaluated in alpha, the cardinality of the graph, and beta, the cardinality of regularity in the graph. Not only that, but there are finally many formulas that tell you which are the possibilities and exactly how it happens, okay? And this is going to be enough to show that any class of graphs with these properties is going to be a multidimensional asymptotic class. And the proof is going to be very similar. You know what is the quantified elimination result in the ultra product. So you know that there is only a certain kind of formula that you have to take care of. You check in the graph that you're using to approximate, and notice that these cardinalities are very easy to measure, and that's it. That's the way you show that this is a multidimensional exact class. So I think I'm running a little bit out of time. So what I'm going to do is to leave a sketch of the proof of this if people ask for it. So let me just end the talk with a couple of remarks about this, about what I discussed today. So a first question / remark is the fact that, I mean, one can ask which nice classes of graphs satisfy the conditions described before for models of TR and TA infinity absolute products, right? And in this sense, I mean, this is a little bit in the same lines of Alice's question. And what I believe, although I have to double check the details and everything is fine, is that there are certain classes of Ramanujan graphs, there are certain classes of expanders and certain classes of sparse, families of sparse graph that naturally satisfy these properties, right? This is work in progress in this semester with Melissa. This is one thing, okay, how the results that I have with Melissa can be extended. However, just talking about pseudo-finite structures, one could ask, okay, once we know that we have a famous example of a pseudo-finite structures, what do we know about the classes of finite structures approximating them? Okay, that's a very natural question. And specifically, what do we know about it being multidimensional, or it being or having a certain control on the sizes of definable sets? And a question that I like, although I mean I haven't given a lot of talk here, is that there is a very famous example of a pseudofinite structures which is called the M alpha. This is the generic limit of the class of graphs with pre-dimension d alpha, which is the number of vertices minus alpha times the number of relations, right? So this is a so-called an amalgamation class, which I know you in Iran know a lot about this. And this example M alpha turns out to be pseudofinite because it can be seen, I mean, it's a little bit like the random graph, although it was shown by Shella and Spencer that it has a 0-1 low and therefore it is pseudofinite. And I think there are some results of Baldwin and Shella giving an accurate description and axiomatization of the theory. So with that in mind, there is a natural question, which is the following. Okay, we know that it is pseudofinite. Which classes of finite graphs can we get? I mean, which classes of finite graphs, interesting classes, can give me M alpha as the ultra product of those graphs? That's one question. And once we know very like interesting classes that do that, one can ask whether or not do I have a control on the definable sets. I believe that this is a rather difficult question in general, but it's good to post it anyway. And another thing that one can ask also, and is part of all this progress, is, okay, once you know there are certain measurability properties, what kind of different constructions can you do to preserve measurability, right? And for example, you can have a structure and consider the H structure this, or you can have a structure and consider now lovely pairs of that. And kind of the point, and this is there is some progress already with in work with Alex Bernstein and Ting-Shen Zhu, where we consider ultra products of one-dimensional symptotic classes. And we show that when you perform the operation of being an H structure, it's normal that the rank goes from SU rank 1 to SU rank omega, but the new structure is going to be a generalized measurable structure. That's what we showed in the last work. And I just want to end with an outstanding result, what I think is an outstanding result of Sylvie Anscombe, because she showed that if M is the Frese limit of a free amalgamation class, then M is generalized measurable, right? That by itself, I think, is a nice result. And notice that there are examples of Frese limit that are not pseudofinite on one hand, but even worse, there are examples of Frese limits. And even worse, there is this example of the generic triangle free graph. Okay, this is an example of something that, if you're familiar with classification theory, it has a TP1 and TP2 theory. So it's a little bit outside of what people think as the tame part of the spectrum. However, we know that it's measurable by the result of Anscombe. And what is even worse is that perhaps the most famous outstanding conjecture in the topic of pseudofinite structures is whether or not the triangle free graph is pseudofinite. We don't know that yet. And the question has been proposed for many years, and even in a paper of Sherlin, he mentioned this question and devotes perhaps a good 20 pages talking about the possibility of the pseudofiniteness for the triangle free graph. And we still don't know. So that's a good question to have in mind if you're interested in these topics. Okay, so I leave you with a couple of references here. And it only, I have to thank you for your attention, for inviting me to give the talk here.
Okay, thank you very much. Thank you very much for your nice talk. Okay, thank you very much. Any questions, comments?
Can I ask some questions?
Yeah, of course.
Thanks.
Go ahead.
Regarding this T infinity, right? And assume that the sequences those came from that operation, lifting operation, right? what would be the polynomials that you mentioned that there is the controlling polynomials? Did you compute them?
Yes, of course, you can compute them explicitly. So if you allow me, probably let me just change the app and use the notes to answer your question. But it's basically like this. So the proof goes in several stages. So the first stage is enough to check one variable, right? That's standard, and it's actually the proof is in a paper of Wolf, but it's very standard. It's enough to check formulas in one variable. Okay. Once you know that it's enough to check formulas in one variable, the second step is to use QE, and QE tells me that the formula phi x y actually looks like an O and I of dki x yi, possibly with negations. So you add this at I, right? So it's this or negations. Then what happens? Disjunctions can be avoided. Meaning, well, if you actually know how to measure these kind of formulas, only conjunctions of formulas and their negations, then it's very easy to do disjunctions, because you basically, what you do is you make the disjunction with a couple more cases so that they are disjoint, and then if the disjunctions are pairwise inconsistent, if you want to measure the formula for the disjunction, you basically measure each one and just add it, and that's what you need. So what I mean with disjunctions can be avoided is that it's only necessary to measure these kind of formulas, right? And also, the fourth stage, let's say, is to notice that the negation of dkxi and the mxi, well, xb, sorry, like this kind of formula, when you have some negation and some positive, it is equivalent to a formula of the form dmxb. Well, actually not this, but negation of and disjunction of dmxb and the jxa. So it's something like this. Like what you do is, if you don't have distance k, then it's the same as saying that you either have distance 1 or distance 2 or distance 3 or distance 4 and so on. There are 3 of them. So with all this analysis, which is very boring, you end up with this. It is enough to know how to measure these kind of formulas. Right? These are the formulas that will pose the problem. And from here, it depends on two things, right? It depends on the possible configurations. What I mean with configurations is distant configurations of the yi's, and possibilities for x. For x regarding yi and yj. It is only necessary to analyze pairs, and that's kind of the point. And it's very similar to an example that I gave before, but let me just explicitly say it here. So for instance, if you are considered the formula being at distance 2 of A and being at distance 3 of X and B, right? So you have A and B. What could happen is that the full distance here is 5, right? 1, 2, 3, 4, 5. There's another point here. So if the distance is 5, then there is a unique point that is a distance 2 of A and a distance 3 of B. You see? So now the polynomial is 1. This is the polynomial. And this is the possible psi, the formula psi of y in this case. Okay? That's one possibility. The other possibility is that A and B are very close. So you have A, B. And in this case, the realizations of this formula are going to be, okay, elements that are a distance from A, right? In this case, you're going to have, the polynomial is going to be, first of all, alpha minus 1 possibilities for the first part, and alpha minus 1 possibilities for the second part. So it's going to be alpha minus 1 squared. And the possible formula, psi, is the 1 of AB. And for the rest is 0. So this is exactly the same example that I analyzed before. My point here, and the point that I wanted to mention when I was talking about the possible configurations of the y's, is that once the elements are fixed, once we know, for example, this is A1, A2, A3, A4, and once we know all the possible distances between them, right? Once we know what is the length of all these paths, once all this is fixed, and when you have this formula, this k A1 dot 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 dk 4 x A2 4, sorry, depending on the configuration, this formula may or may not have realizations, and the possible polynomials that appear have this form. So what happens is that you have, imagine that this is x, a realization of the formula. So there are realizations. What I drew here is the algebraic closure of A1 and A4. And what we know is that whenever you have x and you have this point, if I analyze the paths, there is a single point, I'm going to call it Cx, which is the first point connecting in the algebraic closure that x encounters. So x starts walking here in this path, and this is the first point that it encounters. Once this point is fixed, everything either holds or it doesn't work. Okay, and then the polynomials have this very similar form. So starting from C, so you start, for example, if this is distance 4, then the polynomial will be alpha minus 1 to the 4. But actually, that's a lie. It's alpha minus 1 to the 3 times alpha minus 1 times alpha minus paths in ACL. Okay, so for instance, let me just, perhaps if I give another example, could be better, and I will stop there. This is A, this is B, but now I have the formula being a distance 4 of A and being a distance 3 of B. The only possible way to obtain a realization of this formula is to have something at distance 2 from here. Okay, that's the only way to get a realization of this. Of course, that requires a proof, but it's true. In that case, this is going to be Cx, and the possible polynomial, and the polynomial actually, is going to be alpha minus 2, alpha minus 2, which is, and times alpha minus 1. Okay? Why alpha minus 1? Let me first explain this alpha minus 2. This alpha minus 2 is because from this point, from Cx, I have to consider all possible paths, all possible neighbors, except those that are in the algebraic closure of the parameters, which are these two. That's why it's alpha minus 2. And after I do that, after I take an element that is not in these paths, I can take alpha minus 1 possibilities, right? To get to the point that I want to get. So basically the analysis is all these conjunctions, and the important part is that everything is completely characterized by which is the only element in the algebraic closure that allows me to get a realization, and what is the distance required from that point. Once these two are fixed, this 4, which is the distance between Cx and X, and this Cx is once these two things are fixed, then everything just follows, and all of the polynomials have this feature. Of course, once you have that, you have to add, and therefore they're going to have integer coefficients. And yeah, I think that's it. Sorry for the long answer to that question.
Thank you very
that's
much.
very interesting. Very interesting.